What if humanity is not the first intelligence to rise upon this ancient Earth? The question echoes across the vast corridors of geological time, unsettling and irresistible. Beneath our feet, the stone remembers. Trilobites pressed into shale, their alien eyes staring from 500 million years ago, layer upon layer of stromatolites. The fossilized breath of microscopic architects who painted the seas with oxygen. Billions of years before a single creature walked the land, these relics whisper of a world older than imagination. The story of life is not a line, but a labyrinth. When Charles Darwin first contemplated the origin of species, he peered into that abyss of time and wondered. He spoke of a little pond, where lightning and chemistry might ignite the first spark of living matter. But even Darwin knew, the cradle of life was a mystery deeper than any theory could hold, long before his time. The philosopher Anaxagoras, in ancient Greece, dared to imagine that seeds of life drifted across the cosmos, falling upon worlds like scattered embers. Centuries later, Swedish scientist Svante Arrhenius would give this speculation a name, Panspermia, suggesting that spores of life might travel between stars. Carried on beams of light, protected by the stubborn resilience of microscopic shells. Between myth and science, between dream and data, the idea emerged. Perhaps life did not begin here at all. Perhaps Earth was only a receiver, a vessel for something far more ancient, scattered across space. And if the seed of life itself is older than our world, then who can say what other stories, or other civilizations may have risen and fallen long before our own? Humanity has long placed itself at the center of the story. From the myths etched on clay tablets to the equations carved into chalkboards, the narrative has remained constant. We are the first, the pinnacle, the inheritors of a world that has waited patiently for us to appear. The philosophers of Greece, the clerics of medieval cathedrals, the scientists of the Enlightenment teach in their own way, reaffirmed the same belief. Earth was made for us, and intelligence was a singular flame lit only once, but science has always had a way of unsettling certainty. In the 19th century, when geologists first traced the scars of deep time, they uncovered a planet older, stranger, and less hospitable to human pride than anyone had imagined. The Earth was not a few thousand years old, it was billions. Beneath its surface lay records of ages where human beings had no place, where entire continents had shifted and vanished, and where life itself was erased and reborn in cycles of fire and silence. This revelation carried with it a quiet but devastating implication. If time stretches so far beyond the scale of our existence, then what assurance do we have that we are unique? In a span of 4.5 billion years, could intelligence truly have emerged only once? The Earth is not static. Its surface is a restless ocean of stone, a crust fractured into plates that drift and collide. Continents split, rejoin, and drown in molten seas. Mountains rise like titans, only to crumble into dust. Every 200 million years, the crust recycles itself through the slow churn of plate tectonics. Ocean floors are swallowed into the mantle. Continents are shredded and reassembled. The surface on which civilizations might build their monuments is temporary, fragile, easily erased. What, then, would remain of us in 200 million years? The bones of cities would be ground to sand. The steel of skyscrapers would rust into oblivion. Even the great stone pyramids of Giza, which feel eternal to human eyes, would not survive the slow crush of geological time. Deep history. Even an advanced civilization could vanish without leaving a visible trace. This thought is not fantasy, it is a calculation. Geologists studying the half-life of human artifacts, from plastics to concrete, find that nearly everything we construct is ephemeral when measured against the planet's timescales. Plastics may linger for tens of thousands of years. Radioactive isotopes might remain detectable for millions. But in hundreds of millions of years, the blink of an eye in planetary history all would be dissolved, buried, transformed. This is the first shock. The realization that evidence of past civilizations, if they existed, could be erased so thoroughly that even the most meticulous archaeologist of the far future might never find them. The Earth is not an archive. It is an eraser. From this foundation emerges a darker question, one that turns the famous Fermi paradox inward. The paradox, framed by physicist Enrico Fermi, asked, if the universe is so vast, where are all the other civilizations? Why do we see no sign of them? But on Earth, the question becomes more intimate, more unsettling. What if they were already here? Imagine a species that rose long before the dinosaurs, in the lush Carboniferous forests where dragonflies grew the size of hawks, or one that thrived in the shallows of vanished oceans millions of years before mammals even emerged. Their time on Earth might have been long, their achievements grand, yet their ruins would be gone now, folded into the bedrock or scattered into dust. If intelligence is not unique to us, if it has flickered before and been extinguished, then humanity is not a singular miracle, but a recurring possibility. We may not be the pinnacle of evolution, but simply its latest experiment. This idea strikes at the heart of human pride. For centuries, we have consoled ourselves with the belief that intelligence is destined, that the cosmos produced us to know itself. But the geological truth reveals another possibility. Intelligence may not be destiny at all. It may be fragile, temporary, even expendable. Civilizations may arise not as pinnacles, but as accidents. It's bright sparks in the dark. It's easily extinguished and easily forgotten. And so the second shock emerges: not only could past civilizations have existed, but their absence does not prove they never did. It may prove only that the Earth does not keep its secrets. Scientists have wrestled with this possibility under the lens of what is now called the Silurian Hypothesis, named after a science fiction story of reptilian beings that once ruled Earth. The hypothesis asks, how would we detect a civilization millions of years old? What signs would survive? The answer is sobering. Stone tools, bronze ornaments, and skeletal remains, these vanish quickly. The only traces that might endure are chemical, unusual isotope ratios, synthetic molecules like plastics, or anomalies in carbon deposits hinting at industrial activity. Even these could be mistaken for natural phenomena. This line of thought leads to a third, deeper realization. The silence of the past may not be evidence of absence. It may simply be the silence of erasure. If another civilization did walk this Earth, we may never be able to prove it. And so, the paradox inverts. Where once we asked why the stars remain silent, now we must ask, why is the Earth silent? If intelligence is as natural as life itself, perhaps the silence is not a void, but a veil drawn by time, by geology, by the indifference of a planet that recycles itself endlessly. The unsettling truth is that even our own civilization, global, industrial, immense, might vanish as thoroughly as any that came before. In 100 million years, there may be no trace of us. Our satellites will have fallen, our monuments will be dust, our records, digital or carved in stone, will be unreadable. No beings who walk the earth, then whatever they may be, will wonder if they are the first. They will wonder, as we do now, if intelligence is truly unique, or if they, too, are part of a cycle. This realization casts humanity's place in a fragile light. We are not the inevitable rulers of Earth, but momentary custodians, as vulnerable to erasure as any who may have come before. The geological record is a mirror, showing us both the vastness of time and the impermanence of memory. And in that mirror, we glimpse the most haunting possibility of all, that the silence of the past is not an answer, but a warning. That the absence of evidence is not a comfort, but a shadow stretching forward into our own future. For if Earth has erased civilizations before, it may erase us too. The question of origins has always carried the weight of myth. In ancient tales, life was breathed into clay or sprung from the union of gods. But in the age of science, the mystery remained no less profound. Where in the chaos of a young Earth did the spark of biology ignite? What chemistry gave rise to consciousness? In the mid-20th century, two men sought to turn this timeless riddle into an experiment. Stanley Miller, a young graduate student, and Harold Urey, his mentor, constructed a device as unassuming as it was audacious. Glass flasks, tubes, and electrodes mimicked the primordial conditions of Earth some 4 billion years ago. A closed system contained water, methane, ammonia, and hydrogen, the ingredients scientists believed composed the atmosphere of earliest Earth. They sent electric sparks crackling through the chamber, stand-in for the lightning that once split ancient skies. Within days, the clear liquid turned a murky brown. Inside, to their astonishment, they found amino acids, the very building blocks of proteins. And by extension, of life itself. It was a revelation. From simplicity, complexity could emerge. The experiment suggested that life did not require divine intervention, but might be the inevitable outcome of chemistry and time. Though later refinements showed Earth's early atmosphere may have been different than Miller and Urey imagined, their work opened a door. It suggested that biology may be woven into the fabric of physics, waiting for the right conditions to awaken. From this seed grew the RNA world hypothesis. Long before DNA's double helix came to dominate biology, there may have existed a world where RNA ribonucleic acid was both the blueprint and the catalyst of life. Unlike DNA, which is stable but inert, RNA can store information and also act as an enzyme, speeding chemical reactions. This duality made it a candidate for life's first spark. Experiments revealed that strands of RNA can self-replicate under the right conditions, forming a rudimentary system of heredity. In these molecules, scientists saw not just chemistry, but the first flicker of evolution, the capacity to change, to compete, to persist. If true, the RNA world means that life did not begin in a sudden leap, but in a long dawn, where molecules slowly learned to copy themselves, to make errors, and to adapt. Yet where did this delicate chemistry unfold? One answer lies not in shallow ponds, but in the crushing darkness of the ocean floor. At hydrothermal vents, where magma heats the deep sea to boiling, mineral-rich plumes rise like black smoke. Here, energy flows in abundance. Sulfides and metals precipitate into chimneys, forming intricate labyrinths of pores and chambers. Within these tiny spaces, gradients of heat and chemistry provide the perfect stage for life's earliest chemistry. Modern extremophiles microbes, that thrive in scalding heat and toxic minerals, stand as living testimony. They are not outliers, but survivors of an ancient lineage, perhaps descended from the first organisms that made their homes in these hostile sanctuaries. If life began in such depths, then it may not be a fragile accident, but a robust inevitability. Ready to arise wherever energy and chemistry meet, the search for origins does not end on Earth. Beyond our planet, fragments of stone have fallen, carrying secrets of alien chemistry. In 1996, a meteorite catalogued as a LH84001, plucked from the ice of Antarctica, ignited a storm of speculation. Analysis revealed tiny structures resembling fossilized bacteria, along with organic compounds and magnetite crystals that some argued could only be biological in origin. For a moment, it seemed as though the proof of life beyond Earth was in our hands. The announcement shook the world. If microbes had once lived on Mars, then perhaps Panspermia, the seeding of life across planets, was not a dream, but a reality. Yet skepticism followed. Many scientists argued the structures could be explained by non-biological processes. The debate continues, unresolved, but its impact was seismic. It showed that the line between geology and biology is thin, and that the possibility of extraterrestrial origins cannot be dismissed. Organic molecules have since been found in abundance. The Rosetta spacecraft detected amino acids on Comet 67P. Interstellar clouds contain the precursors of sugars, alkalos, and even simple proteins. Meteorites such as the Murchison Fall carry a cargo of amino acids far richer than those produced. In Miller's laboratory, the universe, it seems, is not barren of life's ingredients, but saturated with them. And so we return to the riddle. Is life an earthly accident or a cosmic inevitability? If the chemistry of biology arises spontaneously, wherever conditions allow, then we may be latecomers in an ancient and universal story. Earth's oceans, its lightning, its vents, may be only one chapter in a tale. It's written across billions of worlds. The ultimate witness to this story is written in the spiral of our own DNA. Within its 4 letters, sadenine, einine, cytosine, guanine lies a history stretching back unbroken to the first cell. Each gene is not just a blueprint for proteins, but a fossil, a molecular echo of ancestry. In our genomes are remnants of ancient viruses, the scars of mutations, the signatures of billions of years of survival. DNA is not only a code for life, it is a time capsule. Its structure reveals common ancestry linking humans to whales, birds to dinosaurs, and all complex life to single-celled organisms that flourished billions of years ago. Tracing it back, we approach the last universal common ancestor, Leucotha, organism from which all known life descends. But beyond Leuca lies a horizon we cannot see. Did life begin here, in the chemical crucible of Earth? Or was it delivered, seeded by the cosmos? The answer may never be fully known, yet the investigation reveals a pattern. Life is persistent. Whether born of lightning in a primordial soup, forged in the furnace of the deep ocean, or carried on the back of a meteorite across the void, it finds a way to begin, to endure, to evolve. This is the second great shock, that life may not be fragile and unique, but ancient and universal, repeating itself across worlds and epochs. The molecules that form our blood and bones may be older than Earth itself, cast adrift in the galaxy before our sun was born. And if that is true, then humanity's story is not only Earth's story, it is a continuation of something far older. A thread woven through stars, planets, and time itself, in every cell, in every strand of DNA, carry the possibility that we are not the first, not the only, and not the last. The deeper science looks into Earth's past, the more unsettling its silences become. Fossils speak, but only in fragments. Rocks remember, but only in the language of pressure and heat. Beyond a certain horizon, the record is erased, rewritten, buried beneath continents that drift like restless ships. Yet the question lingers in that silence. What if intelligence is not unique to us? What if civilizations rose long before our own, only to be swallowed by time? In 2018, 2 scientists, Gavin Schmidt, a climatologist at NASA, and Adam Frank, an astrophysicist at the University of Rochester, to confront this question directly. They called it the Silurian Hypothesis, named after a fictional species of intelligent reptiles imagined in science fiction. The hypothesis does not claim that such civilizations existed, but asks, if they did, would we even be able to tell? The answer is sobering. The vast majority of the physical artifacts of human civilization, our cities, our machines, even our satellites, would vanish in less than 1 million years. The surface of the Earth is too dynamic, too restless to preserve such fragile evidence. Stone monuments might linger, buried under sediments, but even they would eventually erode or be subducted into the mantle. To find the fingerprints of an ancient industrial age, one would have to look not for monuments, but for anomalies, chemical and geological scars imprinted into the very fabric of the planet. Schmidt and Frank proposed that if an advanced civilization had existed millions of years ago, its true legacy would not be ruins, but residues. Carbon isotopes altered by the burning of fossil fuels. Plastics fossilized into strange rocks, forming what geologists now call plastiglomerates. Heavy metals in concentrations unlikely to appear naturally. These are the kinds of signals humanity is leaving behind, today's signals that might persist, faint but detectable, long after we are gone. But here lies the difficulty. Earth has seen such anomalies before, caused not by industry but by nature itself. Consider the Paleocene thermal maximum, some 56 million years ago. The planet warmed dramatically, and carbon isotope ratios shifted in ways eerily similar to the signatures left by modern human activity. Yet no civilization existed then, only mammals just beginning their ascent. The cause was geological volcanic activity, methane release, some other vast natural event. This is the central challenge of the Silurian. Hypothesis: how to distinguish between what nature can do and what only intelligence might accomplish. A massive volcanic eruption can scatter heavy metals across continents. Wildfires can leave soot deposits that mimic industrial pollution. Even plastics, thought to be humanity's most enduring legacy, may not survive the crucible of deep time. Exposed to heat, pressure, and chemistry, they could break down, transform, or vanish into forms indistinguishable from natural polymers. And yet the thought lingers. If Earth were to be studied by an alien civilization millions of years from now, would they see our time in the geological record as a moment of anomaly, a brief, sharp signal in the isotopic archives of stone? Would they wonder if intelligence had once flourished here, only to be erased? And if they would ask that question of us, should we not ask it of our own past? The Carboniferous period offers an especially haunting possibility. No. 300 million years ago, Earth was covered in vast forests of towering ferns and giant horsetails. Oxygen levels soared and dragonflies grew wingspans wider than a hawk's. It was a world rich in biomass. A world that later gave rise to the fossil fuels. Our own civilization burns today. If conditions were so ripe, could intelligence not have arisen then, in forms utterly alien to us? Creatures of chitin and cellulose, perhaps, whose bones and bodies left little trace in stone, or consider the Permian 250 million years ago, before the greatest extinction in Earth's history. Oceans teemed with life. Continents were fused into Pangaea, a supercontinent stretching from pole to pole. If a civilization had emerged then brief, brilliant, and lost the cataclysm that followed, could have erased nearly every trace. The Permian-Triassic extinction obliterated more than 90% of all species. Entire ecosystems vanished. What, then, would be left of an intelligence unlucky enough to exist in that age? It is here that the mystery deepens. Geological time is not only vast, it is merciless. Entire epochs disappear under the weight of erosion and subduction. The surface of the planet renews itself like a palimpsest, written and rewritten, until the earlier words are lost. Against this churn, what chance does a civilization have of leaving a mark? And yet humanity itself is leaving mark scars that may endure. The carbon we release into the atmosphere may shift isotopic ratios for millions of years. Synthetic chemicals, from pesticides to pharmaceuticals, may linger in sediments. Even nuclear activity leaves isotopes with half-lives measured in millions of years. These signals may outlast our monuments, our languages, even our species. They will become part of the Earth itself, indistinguishable from its geology, but subtly different from what nature alone would create. If this is true for us, it could have been true for others. The absence of evidence may not be the absence of existence. It may simply be the consequence of time's relentless erosion. Here, speculation stretches into philosophy. If civilizations have risen and fallen before, what does that make of humanity? Are we a first attempt, or only the latest? In a cycle of creation and destruction, perhaps Earth is not the cradle of a single intelligence, but the stage for many, each appearing, thriving, and vanishing, leaving behind only faint whispers in stone. For some scientists, this idea is less absurd than it sounds. The universe is governed by probabilities, not certainties. Life appears resilient, arising wherever conditions allow. Intelligence, though rarer, may not be unique. If it can arise once, it can arise again. If it has arisen here, why not earlier, in epochs we can no longer clearly see? The Silurian hypothesis does not insist. It only asks. And in that asking, it unsettles. It forces us to confront both the fragility of memory and the arrogance of assumption. Humanity believes itself to be the pinnacle, the first to awaken and to know. But the rocks beneath us, with their long silences and sudden anomalies, whisper otherwise. They tell us that time is long, that erasure is relentless, and that the question of were we first may never be answered with certainty. In this deepening mystery lies the most haunting realization of all. Not that we will one day be forgotten, but that perhaps we were never alone in being forgotten. Life clings to Earth as though it were inevitable. It thrives in deserts of burning sand, in frozen wastes of Antarctica, in radioactive pools where nothing should endure. It seeps into the cracks of basalt miles beneath the ocean floor and floats high in the atmosphere where sunlight is thin. The deeper scientists have searched, the more they have found that life's tenacity seems boundless. And this resilience raises a question older than science itself. If life can exist here in such extremes, could it not exist elsewhere? Could it not travel, survive, even spread across the vast corridors of the cosmos?
Yes.
This idea of panspermia has haunted human imagination for centuries. At its simplest, it proposes that life does not always begin on the planets where it is found. Instead, it may drift between worlds, carried like invisible seeds on the winds of space. Spores, bacteria, or the hardy shells of extremophiles might endure the violence of impacts, the emptiness of interstellar travel, the radiation of starlight. Then, upon reaching a hospitable world, they could awaken, multiply, and begin anew. The possibility no longer feels entirely like fantasy. Modern science has revealed organisms on Earth capable of surviving conditions once thought unsurvivable. Tardigrade tiny plump creatures, no larger than grains of sand, can endure the vacuum of space, lethal radiation, and extremes of heat and cold. Dart. Certain bacterial spores can remain dormant for millions of years, only to revive when touched by warmth and water. If life here can persist against such odds, then the possibility of life traveling between planets, or even stars, becomes harder to dismiss. Yet panspermia is not a single vision. It unfolds in variations, some natural, some deliberate. The Swedish scientist Svante Arrhenius imagined radiopanspermia microscopic spores so light that they could be pushed across space by the pressure of starlight.
Ow.
In this model, life spreads like dust in a cosmic breeze, drifting from star to star.
Leather.
Versions imagine rocks blasted from a planet's surface during an asteroid impact, carrying microbes within them. Protected deep inside, shielded from radiation, they could endure journeys lasting thousands or even millions of years. Before colliding with another world, if this is possible, then the question of life's origin is no longer confined to Earth. Our planet may not be the cradle, but the nursery, one of many places where seeds took root. Perhaps Mars, in its wetter, warmer youth, spawned the first microbes, and meteorites carried them here. Or perhaps comets, ancient wanderers of the solar system, brought with them a cargo of frozen organics, seeding Earth's oceans with the chemistry of life. But beyond natural drift lies a more provocative idea: directed panspermia. In 1973, Francis Crick, the co-discoverer of DNA's double helix, suggested that life on Earth may have been deliberately seeded by an earlier intelligence. It was not a claim, but a speculation, an attempt to explain the improbability of life's origin in the brief window of Earth's early habitability. If abiogenesis, the spontaneous emergence of life, is exceedingly rare, then perhaps it occurred long ago, elsewhere, and perhaps a civilization advanced enough to traverse the stars chose to scatter its biology, ensuring its survival by planting it across the galaxy. The notion is unsettling, for it suggests that humanity may not only be the child of Earth, but the descendant of something far older, born of intentions we cannot know. If true, then every strand of DNA is not only a record of evolution, but a message, carried across space and time. Directed panspermia is not proven, and most scientists view it with skepticism. Yet the very fact that a mind as rigorous as Crick's entertained it speaks to the gravity of the mystery. Supporting such possibilities is the growing evidence that the building blocks of life are not confined to Earth. In interstellar dust clouds, telescopes detect complex organic molecules, amino acids, simple sugars, even precursors of nucleotides. On comets, missions like Rosetta have revealed glycine, the simplest amino acid, and phosphorus, key ingredient of DNA. Meteorites that have fallen to Earth, such as the Murchison meteorite in Australia, are laced with dozens of amino acids, including varieties not found in terrestrial biology. These discoveries suggest that the chemistry of life is not rare. but abundant. The galaxy itself appears to be a factory for organics, scattering them across space, embedding them in comets, asteroids, and planetary dust. If the seeds of life are so widespread, then the emergence of biology may not be a miracle, but a pattern, repeated wherever conditions allow. Here speculation deepens into something vast. If life can spread, then so too can civilizations. Across the billions of years since the first stars burned, how many times might life have taken root, evolved, and reached intelligence? How many times might civilizations have risen, expanded, and fallen, their ruins scattered across galaxies, their memory erased by time? The universe is incomprehensibly old. Our galaxy alone is over 13 billion years in age, while Earth has existed for less than a third of that span. If civilizations arise and vanish in cycles of a few million years, then countless others may have come before us. They may have seeded their biology across worlds, intentionally or not. And we on Earth may simply be one of the harvests of this endless scattering. It is a vision that transforms the silence of the cosmos into something different, not emptiness, but aftermath. A universe where life is not absent but transient, rising like waves and falling again into quiet seas. Each civilization leaves no monuments, only biology, microbes, genes, fragments of chemistry carried onward, woven into the fabric of new worlds. This raises a haunting question. Was Earth seeded once, or many times? Could biology here be a tapestry of arrivals woven from multiple sources? Perhaps early life arose, was extinguished by cataclysm, then arose again, freshly seeded, or sparked anew. Layered like palimpsests in the fossil record of DNA, the mass extinctions that punctuate Earth's history remind us how fragile continuity can be. Each collapse could have been an ending not only of species, but of entire civilizations, primitive or advanced, lost forever to geology's erasure. If seeding is common, then life might not only restart after destruction, but restart differently, each cycle carrying echoes of origins we cannot trace. The implications extend to humanity itself. If life spreads across the stars, then perhaps intelligence does as well. Civilizations may be less like isolated flames and more like constellations of sparks, flickering across time, sometimes overlapping, sometimes alone. We may be part of a lineage that stretches not back for a billion years on Earth, but far deeper into the galaxy itself, into ages and origins we will never fully know. Speculation is not proof. The Panspermia Hypothesis remains debated, its mechanisms unproven, its evidence circumstantial. Yet it is rooted in discoveries that cannot be ignored. The resilience of extremophiles, the abundance of organics in space, the strange possibilities of molecular ancestry. Each fact extends the horizon of what life might be and where it might come from. And in this expansion lies both wonder and humility. If panspermia is true, then Earth is not the singular cradle of life, but one garden among countless others, nurtured by a universe that scatters its seeds with indifference. Humanity's story becomes part of a larger, older narrative, one that may stretch beyond our comprehension, beyond our world, beyond even our galaxy. The cosmic origins of life remind us of a paradox. We are both unique and not unique, both fragile and inevitable. The molecules of our bodies may have traveled across interstellar distances before assembling into life here. Our consciousness may be the latest bloom of an ancient and recurring possibility. And the civilizations we imagine as singular may, in truth, be part of a vast and endless cycle of rise and fall, seeding and renewal, right out across the stars. In this vision, we are not merely earthlings. We are children of the cosmos, heirs to a story far older than humanity, far older than Earth itself. The questions of life's origins, of hidden civilizations, of seeds carried across the stars, cannot rest on imagination alone. Science seeks more than wonder, it seeks evidence. Proof must be coaxed from stone, from ice, from the skies themselves. And so humanity has begun to build its tools, to send them into the void, to drill into the Earth, and to peer into the darkness, searching for answers written in signals too faint for earlier generations to see. One of the first great experiments in this search did not happen on Earth at all, but on a comet. In 2014, the European Space Agency's Rosetta spacecraft became the first mission to orbit a comet, and its lander Philae descended to the surface of Comet 67P, Churyumov-Gerasimenko. There in the ancient ice, it detected molecules central to life: glycine, the simplest amino acid, and phosphorus, a backbone element of DNA, in the frozen dust of a comet. Relics of the solar system's birth, scientists found the same ingredients Miller and Urey once sparked into existence in their laboratory. It was as though the cosmos itself were confirming their vision, whispering that life's chemistry is everywhere, waiting for planets to receive it. Mars, too, has become a testing ground for these mysteries. NASA's Perseverance rover, crawling across the red desert of Jezero Crater, carries instruments designed to detect organic compounds in the sediments of an ancient river delta. Already, its instruments have identified complex carbon molecules in the rocks, suggesting that the raw ingredients for life were once present. In the coming years, tubes of drilled samples will be returned to Earth by a future mission, to be studied in laboratories with the precision of modern chemistry. Perhaps within them lies proof of life, either born on Mars or carried there by the same cosmic currents that may have seeded Earth. But Mars and comets are only fragments of the puzzle. The most powerful tools in this search are telescopes, turning their gaze outward to worlds far beyond our solar system. Through spectroscopy, scientists can dissect the faint light of distant exoplanets, splitting it into rainbows that reveal the chemical fingerprints of their atmospheres. Oxygen, methane, and water vapor, these gases, in certain combinations, could indicate the presence of biology. Already, the James Webb Space Telescope has begun scanning alien skies, detecting carbon dioxide, methane, and even hints of water on planets orbiting distant suns. In time, its successors, the extremely large telescope in Chile, the Habitable Worlds Observatory planned by NASA may probe with such sensitivity that the breath of alien forests, or the exhalations of unseen oceans, become visible across light years. But the search is not only outward, it is also inward. On Earth, scientists are pushing biology to its limits, testing how life might survive the rigors of space. In particle accelerators and radiation chambers, bacterial spores are bombarded with ultraviolet light and cosmic rays, mimicking the violence of interstellar travel. Astonishingly, many endure. Some survive years exposed on the exterior of the International Space Station, shielded only by their microscopic shells. These experiments lend weight to panspermia, showing that microbes could indeed survive journeys through the void, embedded in rocks ejected from planets or drifting within comets. Beneath the surface of Earth itself, drilling projects extend the search backward in time. In cores pulled from ancient sediments, scientists analyze isotopic ratios, chemical anomalies, and fossilized microorganisms. They search for signs that life's story may not be as linear as it seems, that perhaps there were episodes of complexity, erased before the Cambrian explosion. Precambrian anomalies, chemical shifts without clear biological explanation, haunt the record, hinting at stories half told. In these deep cores may lie traces of forgotten experiments of life, or of catastrophes that reset the clock. Wiping away entire biologies before ours arose, the pursuit of technosignatures extends the search beyond biology into the realm of civilizations. Radio telescopes listen for structured signals against the static of the cosmos. Infrared observatories search for excess heat that might betray vast machines. Dyson spheres or other technologies consuming starlight on a cosmic scale. Though no definitive signal has yet been found, the effort itself reflects the recognition that life may not only survive, but thrive, advancing into forms as invisible to us as we are to trilobites in stone. Future instruments will sharpen this search into something unprecedented. The James Webb Space Telescope has already begun to reveal worlds cloaked in chemistry, but it is only the beginning. The extremely large telescope, with a mirror 40 meters wide, will resolve exoplanets directly, searching their atmospheres for the delicate balance of gases that may signal life. The Varese-Rubin Observatory will scan the night sky in rapid cadence, detecting transients, flashes, and movements that could hint at artificial structures or activities. Even more ambitious, projects like Breakthrough Starshot dream of sending nanocraft to nearby stars, carrying cameras and instruments on beams of light. Such probes could, in time, peer directly into the skies and oceans of alien worlds. The testing is not limited to astronomy. In the laboratories of Earth, scientists are exploring the boundaries of molecular ancestry. By sequencing genomes across species, they attempt to trace the tree of life back to its root. Yet at the base lies a veil, the last universal common ancestor, Luca. Beyond it, the record fades. But with each new gene sequenced, with each molecular fossil discovered, scientists edge closer to answering whether life began here once, or began many times, seeded anew after each extinction, perhaps from beyond Earth itself. The search is vast, spanning the cosmos and the microscopic, the past and the future. It requires machines that can endure the cold of comets, the storms of Mars, the faint light of distant stars. It requires drills that pierce rock older than any mountain, and accelerators that recreate the fury of space. Each experiment is a hand extended into the unknown, reaching for a fragment of proof. And yet, the deeper the search goes, the more profound the questions become. If life's chemistry is found on comets, is that proof of panspermia, or simply of universality? Traces of biology are found on Mars. Will it be evidence of a second genesis, or of a shared origin carried by meteorites? If biosignatures are detected on distant exoplanets, will they reveal thriving civilizations, or only microbial seas? Science advances carefully, aware that extraordinary claims demand extraordinary evidence. But even as definitive proof remains elusive, the tools themselves are changing the way humanity perceives its place. No longer is Earth seen as an isolated cradle. It is part of a network of worlds, each potentially linked by chemistry, by biology, by history written in molecules older than stars. Perhaps the most haunting realization is this: even if life is found elsewhere, or even if traces of ancient civilizations are someday unearthed in Earth's own record, the evidence may be subtle, ambiguous, contested. The truth may never arrive as a clear revelation, but as a mosaic fragments pieced together into a picture that can never be whole. And so the search continues. Telescopes gaze outward, drills pierce downward, experiments stretch the boundaries of survival. Humanity listens, measures, waits. Proof may come tomorrow, or in centuries, or perhaps never at all. But the very act of searching transforms the question from myth into science, from speculation into pursuit. For in building these tools, in straining to hear whispers in the dark, humanity affirms something profound, that the mystery of life's origins is not only a question of science, but a reflection of who we are. Species compelled to ask, compelled to seek, compelled to wonder if we are alone, or if we are only one voice in a choir that spans the galaxy. Civilization feels enduring. Cities of stone and steel appear immovable, their monuments stretching skyward as if to defy time itself. Yet in the grand scale of Earth's history, such confidence is an illusion. Civilizations are fragile phenomena, brief arrangements of matter and thought that flare brightly before they vanish. The planet has seen countless empires of biology rise and fall, each erased by catastrophe. Humanity, with all its technology and ambition, is not immune. The story of extinction is etched deeply into the rocks beneath our feet. 250 million years ago, during the Permian extinction, the Earth itself convulsed. Vast volcanic eruptions in what is now Siberia poured rivers of basalt across millions of square kilometers, releasing greenhouse gases that warmed the planet to deadly extremes. Oceans lost their oxygen. Methane seeped from the seafloor, amplifying the catastrophe. In the end, more than 90% of all species perished. The biosphere itself nearly collapsed. Whatever fragile experiments of intelligence might have existed before were erased without trace, swallowed in a silence that lasted millions of years. 65 million years ago, catastrophe struck again. A mountain-sized asteroid slammed into the Yucatan Peninsula, gouging the Chicxulub crater and sending dust and sulfur into the skies. The earth darkened, plants withered. The great reptiles, rulers of land and sea, fell into extinction. Yet from that devastation came an opening, a chance for mammals to expand, adapt, and eventually give rise to us. Catastrophe is not only an end, but a reset and erasure that clears the stage for something new. What these events reveal is a pattern. Extinctions are not rare accidents. They are woven into the rhythm of Earth's history. At least 5 major extinction events have swept the planet clean, each reshaping the trajectory of life. Some were triggered by impacts from the sky, others by the fury of Earth's own geology. One demonstrates how precarious survival is, even for the most dominant of species. This fragility extends beyond biology to intelligence itself. If civilizations arose before humanity, they too would have faced the same gauntlet of catastrophes. An industrial society flourishing in the Carboniferous might have fallen to the Permian cataclysm. Culture born in the warmth of the Triassic might have vanished in the chaos of the Cretaceous impact. Even an advanced intelligence cannot outlast a planet's indifference. Time and geology erase equally, with no regard for complexity or ambition. The concept of the Great Filter crystallizes this unsettling truth. In the search for extraterrestrial civilizations, scientists have long puzzled over the silence of the stars. If life is common and intelligence inevitable, then why do we see no evidence of other civilizations? Why is the universe not crowded with signals, artifacts, or structures of alien origin? One possible answer is that somewhere along the path, from simple life to galactic society, there exists a filter, near insurmountable barrier that most civilizations cannot pass. Perhaps the filter lies in the rarity of life's beginning. Perhaps it lies in the leap from simple cells to complex multicellular organisms. Or perhaps, most ominously, the filter lies ahead of Wusin, the fragility of civilization itself. If intelligence tends to destroy itself through war, ecological collapse, or technological hubris, then the silence of the cosmos is not surprising. It is the silence of civilizations that burn too brightly and too briefly, leaving no trace in the abyss of time. Humanity, for all its achievements, walks this knife's edge today. The threats are many, some born of the cosmos, others of our own making. Asteroids continue to cross Earth's orbit, silent reminders of the Chicxulub catastrophe. Supervolcanoes simmer beneath the crust, capable of darkening skies and chilling climates for decades. Nuclear weapons, creations of human hands, hold the power to erase entire nations in an instant and to plunge the planet into a long winter of ash. Climate change, driven by the burning of fossil fuels, reshapes ecosystems and raises seas, echoing in miniature the upheavals that once ended entire ages. These dangers remind us that intelligence does not guarantee survival. Knowledge does not protect against hubris. Technology, while granting power, also multiplies vulnerability. A species capable of altering its climate, of splitting atoms, of engineering pathogens, must also confront the possibility that its own ingenuity is the instrument of its end. If we are not the first civilization on Earth, then perhaps others, too, reach such thresholds. Perhaps they mastered fire, mined their planet, altered their atmosphere, and in doing so, set in motion forces they could not control. Their traces would be gone now, erased by geology and time, leaving only the lesson. Intelligence alone is no safeguard against fragility. This is the philosophical weight of the Great Filter. It confronts humanity with a mirror, showing both its promise and its peril. On one hand, our existence proves that the barriers to life and intelligence can be crossed. On the other, our silence in the cosmos suggests that survival beyond this point may be rare. Civilizations may not last long enough to broadcast across the stars. They may vanish into their own ruins, their signals lost, their monuments buried. their names forgotten, and so the haunting possibility arises. Humanity may be part of a repeating cycle. Life emerges, evolves, ascends, and is erased. Catastrophe resets the stage. Another chance begins. Over the eons, intelligence may have flickered on Earth not once, but many times, each instance extinguished before it could endure. The silence we perceive in the fossil record, in the geological archives, may be not the absence of others, but the consequence of their fragility. This realization brings humility. Civilization, for all its triumphs, is not eternal. It is provisional, conditional, balanced against forces far larger than itself. The planet remembers extinctions, not monuments. Time remembers erasure, not permanence. The great filter is not an abstraction. It is the shadow of history, the reminder that survival is the rarest achievement of all. Humanity stands now at its own threshold, aware of the dangers, capable of foresight, yet uncertain of its resilience. Perhaps this awareness is itself the test. To endure, a civilization must not only harness knowledge, but wisdom to understand its fragility and to act accordingly. If it fails, it will join the silence of those who may have come before. If it succeeds, it may step beyond the filter into a future where intelligence can last, and where the questions of origin and destiny may finally be answered. But for now, the lesson is clear. Civilizations are fragile, as temporary as the creatures that build them. The Earth will endure, the cosmos will continue, but whether humanity will join the long silence or break it remains unknown. The Earth remembers nothing of certainty. Its mountains rise only to fall. Its seas advance and retreat. Continents drift, fracture, and merge. Even stone, which feels eternal to human hands, is only a temporary arrangement in the endless churn of time. Against such immensity, even the greatest monuments of civilization are fragile, skyscrapers and pyramids. Libraries and cathedrals all are brief patterns etched on a surface that erases itself every few 100 million years. What endures is not the memory of civilizations, but the rhythm of their vanishing. This humility of time forces a deeper reflection. If Earth's surface can so easily bury the evidence of our own achievements, then what of those who may have come before? If intelligence has flickered in ages past, its traces would be scattered, ground to dust, folded into stone. Civilizations could rise and fall, not once, but many times, each erased before the next begins. And if life is seeded across the cosmos, then Earth itself is not singular, but one garden among countless others. In this view, we are not the pinnacle of creation, but a chapter in an older, larger story, a story whose first pages may forever be lost. What does it mean to live within such a cycle? It means that permanence is an illusion. The memory of humanity, however deeply carved, may not outlast the slow patience of geology. Even the written word, which once promised eternity, fades into silence. Data stored on fragile media will vanish. In decades, stone carvings will crumble. DNA itself, the most durable archive we possess, will unravel in time. The fragility of memory against the immensity of the planet is humbling. We may desire to be remembered, but the Earth does not remember. It transforms. And yet, the paradox emerges, though we may never know if we are the first. The pursuit of that knowledge defines us. The act of asking, of searching, of stretching thought into the deep past and the distant future is what sets intelligence apart. Even if the answer is silence, the question itself is a kind of immortality. To wonder is to exist beyond the present moment, to situate ourselves in a story larger than any one life, larger even than any one civilization. Science teaches that. Life may be ancient, seated across galaxies, resilient against extinction. If this is true, then humanity is not alone in possibility, even if it is alone in knowledge. We may be part of a lineage that stretches not only across Earth's history, but across cosmic history, bound by molecules that formed in the hearts of dying stars. To live with this awareness is to accept both insignificance and connection. Insignificant in the face of time, yet connected to everything that has ever lived. In this light, impermanence is not despair, but clarity. The very fact that civilizations can vanish reminds us to act with care, to recognize that survival is not guaranteed. The possibility that intelligence has risen and fallen before does not diminish us, it deepens the meaning of our moment. We may be one spark in a sequence of many, but this spark is ours to tend. Perhaps the silence of the past is not only a warning, but an invitation to endure, to choose differently, to build a civilization that does not collapse under the weight of its own ambition. If others failed, their failures need not be ours. If time erases, then perhaps our task is not to outlast time, but to live with awareness of its power, to know that impermanence does not strip life of meaning, but grants it urgency. And so, humanity stands at the edge of its own abyss, aware of its fragility, uncertain of its permanence, yet still reaching upward. Telescopes scan the skies, not because the stars promise answers, but because the act of looking makes us more than fleeting creatures. Rockets climb into the heavens, not because eternity is ours to claim, but because the journey itself defines us. In the end, the meaning of life may not be found in survival, nor in monuments, nor even in memory. It may be found in the reaching itself, in the refusal to accept silence, in the desire to ask, to wonder, to search. The pursuit of the unknown is humanity's true inheritance. The one legacy that geology cannot erase. The story closes not with certainty, but with reflection. We may never know if we are the first, may never know if others rose and fell before us. We may never know if the cosmos is filled with civilizations that flicker and fade, leaving only whispers in stone and starlight. But we know this: we are here now, alive in a universe that allows us to ask. And in that asking, we are part of something larger than time. Civilizations may vanish, monuments may crumble, memory may fade. But the act of reaching for the stars, of gazing into the abyss, and daring to wonder, is itself eternal. Humanity stares into the darkness of its own impermanence, and still it reaches.